April of 2009. We have people talking here about Arctic gas hydrates and global warming, a very hot topic. And we have Treude from Geomar in Kiel, I will say it correctly now. We have Matthias Haeckel also from Geomar.
Yep.
Oh, yeah. Christian Hensen from, I don't know which.
Same. The same. We are all three from the same.
Okay, fine. And something.
And Graham.
Graham
Westbrook. Yes.
Yes.
Okay. Well, Tina,
from University of Birmingham in England, not from...
Not from here.
Okay, thank you. Tina, you will do the first introduction. Great. Okay. Up to you.
Yeah. So welcome everybody, and today we're going to tell you a little bit about how exciting gas hydrates might be as a potential energy source and why it is interesting, and how we could use maybe also gas hydrates to store CO2. And finally also why gas hydrates are under discussion now, how they could become a climate disaster. But first of all, I would like to introduce my colleagues. So first of all, I start with the IFM Geomar round. So if you have any questions, so we are all experts on different fields. So Christian Hensen is expert when it comes to production, to quantification of gas hydrates in the natural system, in the marine system. He's a geochemist. And then we have Matthias Haeckel, if you have any questions when it comes to CO2 sequestration or production of methane from gas hydrates. So he's the one you could ask. And I myself, I'm a biologist, so I'm more interested in the biological reactions, microbial reactions that are connected with gas hydrates and methane releases. And then we have Graham, who's visiting us today from University of Birmingham. And he's a geophysicist and is an expert on gas hydrate exploration. So Graham will give a short introduction of some of the recent findings they made recently of Svalbard after our introduction. So you see a little movie here, which is running while I explain a little bit about gas hydrates. So when we want to discuss why they are a potential energy resource, you have to understand what gas hydrates are. And you see here this ice-like structure, and when you go further close up, you will find that we have always one gas molecule that is sitting in the cage of water molecules. So in natural, when you have gas, free gas, then the molecules are very distant from each other, but here they are in a compact form. So that means when you melt gas hydrates from about a liter of hydrate, you would receive a huge amount of gas, like around 180 or 190 liters. And you will also have the release of water. And this gas can be different kind of gas. In most natural systems it's methane. It can be also CO2, so carbon dioxide. And also like higher carbon molecules that are gasiform. And here it's demonstrated very nicely why gas hydrates are a potential energy source. So if it's mostly methane, then you could gain a gas that you could use for cooking, for burning, and heating, and so you can basically burn it and the water will rinse through your fingers, although you have something burning in your hand. And what is also important to know is how gas hydrates are forming and under which conditions. So there are two factors that are to mention, and that is hydrostatic pressure and temperature. So this is a very simplified sketch here showing that you have, if you want to have the formation of gas hydrates, the temperatures have to be either very low when you are at like ambient pressure, so places like Arctic systems or so, where you have very cold temperatures, or when you go to the open oceans where you have temperatures around 4 degrees in the deeper parts, then you need high hydrostatic pressure to have them stable, so around below 500 meters in the open oceans they are stable. And this is an example to show you what this means if you go to a natural system. This is an example from the Black Sea, where you see here this is the stability line, so below 725 meters gas hydrates form and are stable. And above that they are unstable, and what you see here are little flares. These are gas emissions from gas resources in the seafloor, and since they don't form gas hydrates that are solid, the methane can escape, whereas here you have the formation of gas hydrates and you have no bubbling of gas out of the seafloor. And when we look on the global map and look where we find gas hydrates, so these little dots you see here are all like fields that have been explored. And from the distribution you see that most discoveries of gas hydrates were made along the continental margins or in places where we have permafrost, very cold temperatures. And we find gas hydrates very rarely in the very deep sea, and one reason is that if gas hydrates form, they form from methane, which has been produced during organic matter degradation, and in the deep sea not much organic matter reaches these deep water depths. So methane hydrates you find very often at continental margins where pressure is high enough to form hydrates and where you have enough organic material to form fossil methane reservoirs. And this is a little overview about exploration activities of different countries and when it comes to gas hydrate exploration, and you will recognize that especially countries that don't have much own energy resources are today interested in gas hydrate exploration. So people are thinking of producing gas from gas hydrates in the ocean or on the terrestrial system where we have permafrost. So you will get these slides later if you want, so you don't have to write down like all the details. And another thing that is interesting about the formation of gas hydrates is to use them as a way to store carbon dioxide, so CO2. And what you see here are two stability curves showing under which conditions methane are stable as gas hydrates and carbon dioxide. And what you see here is that carbon dioxide actually forms hydrate faster than methane, so you need less pressure or you can have it at higher temperatures formation, so it's actually more stable than methane hydrate. And this could be used for maybe storing CO2 in the ocean systems in depth where gas hydrates are stable, so CO2 hydrates. And an even more advanced idea is that not even only store CO2, but inject CO2 and remove methane from inventory at the same time. So you would gain energy and you would sequester CO2. And if you have any special questions on that, then you might talk to my colleagues from IFM Geomar here who are involved in projects doing that. And this is just an example to show you how people imagine on this way of storage of CO2. So here we have places where gas hydrates, CO2 hydrates, would be stable at the continental margin, at the deep sea. So if you inject CO2 there, it would form hydrates with water, and it's solid and it's will not release any CO2. If you want to inject CO2 at shallower places, then you would need a cap rock, something that is would not enable the CO2 to move out of the system because it will not be stored as gas hydrate, but in this case either as liquid CO2 or as CO2. And last but not least, I will come to that issue, why could gas hydrates become a potential climate disaster? There's a lot of debate going on in gas hydrate dissociation caused by global warming. And I want to go back to this sketch here and remind you that the problem could be with gas hydrates that when temperatures rise, that they are getting unstable because one parameter that makes them stable is temperature. And if you have very low pressure regime, so very low water depth, like in Arctic Ocean, then it might be even more sensitive to temperature changes. And this is showing a report from IPCC where you see that actually scientists observe an increase in water temperatures in the ocean. This is from 0 to 700 meter water depth, and so this is a direct correlation also with the atmospheric temperature rises, and you see then also temperature rises in the ocean waters. So how could we imagine now what could happen when temperature rise in the ocean water column, and what happens to the gas hydrate? So what you see here is a sketch showing how we can imagine the situation now. So we have a certain depth, the stability depth under which gas hydrates are stable. Above that we would have the release of gas. And when we have now temperature rises, the stability zone would be shifted into larger depths. So you need higher pressure to have gas hydrates stable at a higher temperature. And so the gas hydrates would probably melt in this depth and then release the gas into the ocean. And what's happening to that gas, that's something that we're also investigating. And just to give you that example back from the Black Sea, if we imagine what you have seen here, which would be the stability zone, the old stability zone, if we have global warming and then warming effects at the sea floor, we would maybe have something like this, that we get a new stability depth, and then we would find also gas flares at this depth here with rising gas bubbles from the methane source. And then finally I would like to come to the place where we think that it's most sensitive for gas hydrate destabilization, and that is the Arctic Ocean. What's so special about the Arctic Ocean is that due to the low temperatures, gas hydrates are stable at relatively shallow water depth, and we think that a lot of methane is currently locked up in the seafloor as gas hydrates or in permafrost. And you see here that the Arctic Ocean is surrounded by huge amounts of shelves, so shallow regions. And if we imagine that if temperature rises, the gas hydrates in these shallow regions could partly destabilize and release gas into the water column and maybe also into the atmosphere. And since methane is a greenhouse gas, very potential greenhouse gas, about 20 times more potent than CO2, it could further boost the global warming effect. But the question is also, like, is there something that prevents the emission of this methane into the atmosphere? And good news is actually there is a very effective process in the ocean that consumes a lot of the methane before it enters the atmosphere. And this is, to one part, microbial activity. So we have microbes that live in the sediment and another type of microbe that lives in the water column that consume the methane. So actually the oceans are producing a lot of methane, but not much reaches the atmosphere today. But what we don't know, and what is a little bit problematic with these microbes, is that first of all they cannot access gas bubbles. So first of all the gas has to be dissolved into the water, so either into the water column, or when we're talking of sediment, into the pore room, to pour water of the sediment, so that they can consume the methane. The other problem is that especially those in the sediment, they grow very slowly. So if temperatures are rising, if gas hydrates should melt quickly, we don't know how fast this microbial filter can react on the changes, on this higher methane transport. And so what scientists are doing now, there are a lot of ongoing projects at the moment doing gas hydrate investigations in terms of production, of CO2 sequestration, and also all these climate aspects. And so what we are doing is, first of all, we are monitoring critical regions like continental margins and Arctic oceans. We are conducting experiments in the lab on the formation and dissociation of gas hydrates to see what reactions can we expect. And we're doing field experiments and also lab experiments to study the geochemical processes in the sediment and how the microbes react to gas fluxes. And then we apply also models. So we do modeling of gas hydrate dissociation scenarios. And this is topics that we, in this year EGU session of gas hydrates, we will cover and discuss with our colleagues. So thank you very much. And so then I would hand over to you. And then we could do the questions at the end, I think. So intro. We want to change maybe the places?
No, it's okay, I think, I hope. Oh, you were using it, you're controlling it with this, weren't you? Well, first, oops, I think there's a bit of resonance here. The title that I put up here is the title of the talk that I'm giving in the session tomorrow on behalf of my co-authors given here. And where we have been working, and this was in August and September of last year, is essentially offshore of Svalbard, which is, as you can see here, well into the Arctic Ocean. And there's one important aspect about Svalbard and its situation is that it lies at the northern end of the Gulf Stream system. And here, that warm current called the West Spitsbergen current washes along the continental margin here and goes into the Nankai Nansen Basin. Nankai's off Japan. And there's another branch which goes up here through the Barents Sea too, but this is the main one. So this is in more detail, and I won't go into all the details of the...
Want to have the pointer? It's here.
Okay. But you can see here that where we've discovered evidence for gas escaping from the seabed lies here on the continental margin offshore Svalbard. Basically the West Spitsbergen current is going along northwards in the past here, and the depth at which the hydrate stability field that Tina spoke about just now, essentially the landward limit of it, is at about the 400 metre contour, which I've marked here in red, this contour just here, just in the middle of the steep part of the slope as we go along in that direction. So what I'm going to show you next is the results that we obtained in part of this area using a sonar system. In fact, it's a fish-finding sonar system, that's what it's designed for, but it's very good at picking up the backscattering from bubbles. And in this view, it looks really rather messy because you can see the lines of the survey going along like this. Okay. And also, we're finding lots of fish and other things. That's what the sonar's designed for. But in addition, you may also see these things growing up, apparently growing up like trees, Christmas trees from the seabed. And these are actually plumes of gas bubbles. You can see that the bases of them are quite high intensity. They don't actually thin upwards in this way. The apparent thickening downwards is an artifact of the beam, the actual beam angle of the sonar. So it sees more at deeper depths than it does at shallower depths. But you can see that in this view alone there are many tens of these plumes. They're also leaning over towards the north. This is because the current is carrying them towards the north, so they're not coming up vertically. The bubble plumes are leaning over. Bubbles are rising at about 25 centimeters a second, that kind of speed. And in here, oops, let me just go back. And you note that I identified this position CTD10. CTD stands for conductivity, temperature, depth. It's a standard oceanographic measurement. You let down a system which measures the conductivity, the temperature and the depth that allows you to assess the salinity. You often measure other things at the same time, like oxygen content. And also, typically, a rosette of water bottle samples would be attached to this system so that you can take samples of the water and measure what's in the water. So what I'm showing on the left-hand side here are the variation in methane content coming from the water bottle samples going downwards. And you can see that it's increasing downwards to a value about here, which is about getting on for 20 times the background value. Also illustrated is the temperature. And notice that the temperature increases downwards generally, but once it gets to here it has a little kink, starts increasing again, and then becomes, sorry about this, I'm going the wrong way. I'm pressing. That's it. I don't know how to use yours, that's the problem. But below here it's about constant temperature, and if we looked at the salinity curve that would also show the same thing. Then if you track across to the thing on the right, here is a blow-up of these acoustic images of the plumes. And basically the red-coloured, orangey-coloured blobs are the highest intensity backscattering. And you can see this plume reaches pretty well to the sea surface as far as we can tell. This one doesn't go so far. And the CTD position is in the middle. And you can see here it just goes into the edge of the plume when we get that little kick. And then below this depth it's entirely within the water in which the bubbles are ascending, and we get this behaviour which is caused by the mixing and entrainment of the water as the bubbles rise to the surface. So there's a clear anomalous methane content in the water associated with these bubble plumes. So this is a diagram, perhaps just a little bit more detailed than the one that Tina showed about the hydrate stability zone. She mentioned to you that it's controlled by temperature and also depth, which is controlling the pressure. And within the water, I don't know why it does that, that's fairly easy to, the pressure just goes up fairly normally with depth. And in general, actually, temperature gets cooler as you go down within the water column. But once you go underneath the seabed, temperature rises. It rises anywhere between, say, somewhere like 20 degrees centigrade per kilometre to, well, quite a lot depending where you are. In fact, further down this slope, the temperature gradient, because it's close to a volcanic ridge, goes up to 100 degrees centigrade per kilometre. Here it's probably around 40 or 50. And so as you go down, you come to a boundary which is the base of the hydrate stability field, because below that depth the temperature is too warm to sustain the hydrate. So we essentially have this triangular shaped zone, top of which is in the water, the bottom of which is in the sediment, in which hydrate is stable. And then we have this edge of it. Well, the correlation in our work is that it's at this edge where we predict it from the theory that we start to see the plumes. And these plumes then extend landwards at least 10 kilometres. So these plumes are coming out in an area where the hydrate stability field no longer exists. And it's obvious because of the distance over which they occur that there's some deep source of methane coming out. But downslope of this edge we find maybe the odd one or two very close to the edge. We don't find any plumes. So basically the hydrate stability field is governing the way in which the methane escapes from the seabed. It's capturing the methane within the hydrate stability field, turning it into methane hydrate, and probably also acting a bit as a barrier and diverting some of the methane to migrate upslope if the geological structure helps this. And in general it does. The dip of the strata is as I've shown it. So that would be the simple situation. The hydrate stability field is acting as a reservoir, a sink, a storage of hydrate, and something as a barrier. But this doesn't take into account any climate change. And what we also did is we looked at the oceanographic data for temperature in this region over in fact, just over a 30-year period. And the positions of all the CTDs from which these measurements are shown as the dots, and the colours show the year in which they were taken. So this colour scale shows the years from 1975 to 2009, none in 2009 by the way, the latest ones were last year in 2008. And the area in which we saw the plumes is indicated here. If we look at a simple illustration of this, that's just a graph showing all those curves plotted together. And in the middle is a black curve which shows the mean one. But I hope it's noticeable that if you look at the lower temperature side, they're all in the blues and things which are the early years, and all the high temperatures are all in the later years. And we've analysed this a little bit more systematically than just plotting a graph, essentially by a bivariate regression against time and depth, because there's a depth effect as well, to see the temperature change with time. And it's about 1 degree centigrade over the last 30 years. So this specific place, we're not talking about the Arctic Ocean in general, which is also known to be warming, but this part of the West Spitsbergen current has warmed by this amount. And so we then calculated, okay, if it's warmed by 1 degree centigrade, in fact the temperature's gone up from 2 degrees to 3 degrees centigrade over the past 30 years, what would have happened to the gas hydrate stability zone? And here's a simple illustration of it. You can see that essentially at 0 years it's up here, 30 years later it's migrated about a kilometre down slope. And a more colourful illustration there would be this, with the dashed line showing the former position and the solid line showing the current position, this zone once had hydrate in it, and any hydrate that was there will have dissociated completely. There's no way that it could exist anymore. That methane has to escape. And because 30 years is a relatively rapid change, that methane probably escapes quite quickly into the water column, which is why we have this concentration of plumes close to the edge. Although, as I said before, there are plumes from the background source of methane going a few kilometres inland as well. What happens to the methane? It goes up into the water. We can see the bubbles going into the water. We know that most of the bubble plumes don't even get to the sea surface, but a few do. But also work that not we did on the cruise, but on similar bubble plumes, like the ones you saw illustrated in the Black Sea earlier, show that also as the bubbles go up, they exchange methane with other gases in the water column, such as nitrogen and oxygen. And so even though we see bubbles coming to the surface, they might not actually have methane in them any longer. But if they're coming out quickly enough, rapidly enough, then they can make it to the sea surface. We don't actually know how much of that gas at the moment is making it to the sea surface. But we can make some estimates about how much gas is being released from the hydrate to the water column. So what we did is we just had a look at, in pink, within this white box, all the area that lay within this, if you like, zone of transient in which it could have retreated. And I should have mentioned in the last one that just in the area which we were working at, we estimated there was about 27 kilotons of methane per year. But if we extend it to this large area, that's about 20 megatons of methane per year. The Earth's global budget of methane per year is somewhere between 500 and 600 megatons a year. This is only a small proportion of the Arctic continental margin. And we might think, oh dear, something is really happening. But what I would say is that, for instance, there is an international methane monitoring station actually sitting on Svalbard here at Ny-Ålesund. Really large signatures of methane entering the atmosphere have not been detected. So either we are wrong in assuming how much of the seabed has hydrate in it, or most of that methane is being dissolved in the water and oxidized to some extent before it actually reaches the surface. However, what we also did is we measured on this cruise the amount of methane in the atmosphere compared with the amount of methane in the water. And everywhere in this area, the concentration in the water was higher than in the atmosphere. And that means that there is a certain amount of methane transfer by diffusion all the time across the water-air boundary. It's all the time exchanging. But we don't think at the moment the signal, the amount of exchange, is very strong. But this is just one cruise's sample. This is like, 4 weeks in late August and September. We don't know how this changes on a cyclic basis during the year. We know from methane plume areas in other parts of the world that they can go for periods that are sort of like a sort of intermittent, semi-constant activity, and then every so often have really catastrophic outbursts where the amount of methane coming out in one go over a few hours and days can be equal to all the methane discharged from the whole area in the previous few years. And it may be those kinds of catastrophic events which are the ones that really push the methane into the atmosphere. I can't say that one of these will happen. All I know is that in other places of the world this kind of behaviour has been observed. We have not yet observed anything like this so far in this part of the Arctic. That's all I have to say for a moment. Oh, sorry, yes. There's some summaries. Pretty well just going through. We saw at least 250 methane plumes. This is conservative estimates. I won't go through how they... And they were mainly detected using this fish finding sonar. You can see them with sonar at other frequencies as well, but this was the most sensitive. We know it's methane because we took samples with water bottles and measured the chemistry, so happy about that. Also, we know that salinity and temperature are disturbed by the plumes. Also, another thing, that the transparency of the water is decreased in the plumes as well because of the disturbance by the bubbles. Why are we sure that we actually sampled them? Because the ship we were using, the James Clark Ross, has dynamic positioning by satellite. The actual CTD thing that we measure lower down on a wire has an acoustic beacon on it, which is located by an acoustic navigation system on the ship, so we can maneuver the ship to be pretty well on top of the bubble plume. So although we didn't actually visually identify bubbles of gas going into our sampling system, which you can do with more sophisticated systems like ROVs, we're fairly sure that we got good samples, at least of the water in which the bubbles was coming up. This zone of bubbles extends at least 10 kilometres away from the edge of the hydrate stability zone, so we're measuring part of a natural system which is letting methane into the water anyway. But the hydrate stability zone acts as a barrier and a sink, a storage of methane once the hydrate stability zone appears, and it does appear that warming of the West Spitsbergen current by about 1 degree centigrade over the last 30 years has caused a fair amount, I'm saying it rather vaguely at the moment, but certainly some hydrate to dissociate in this region. We know that further downslope we have concentrations of about 4.5% on average in the pore space. And if we were to extend that estimate into this area, where there is also evidence for gas in the sediments, which I haven't shown you, but if you came to the talk tomorrow, you'd see it then, that little area that we were looking at, about 20 kilotons per year of methane, for the whole of the Svalbard archipelago, all those islands, 20 megatons. But the catastrophic methane effect of methane on the climate isn't immediately apparent in this area. At the moment, it seems that the water is stopping most of it getting out. Thank you.
Well, thank you very much, Graham. We have time for a few questions, so you can
That was from the cruise on the James Clark.
That's right. Yes.
When was that?
It was late August and most of September.
But at the same time, when I think a Russian.
That's right.
Discovered.
Yes, in the Laptev Sea. Yes. And that's quite interesting because it received a lot of press attention at that time, and it was reported in the press, the Independent as it happens, that bubbles were seen coming to the sea surface, etc. So we were very interested in that, and later in the year, when I saw Igor Tsemelitov, who was one of the principal people running that cruise, about the bubbles, I have to say that he said that he individually didn't observe any bubbles coming to the sea surface, although he said some of his colleagues did, but he wasn't sure that they were bubbles. They thought it was just cavitation. However, what I would say is that what they demonstrate very clearly from the work is there's a large amount of methane in solution in the water column. In fact, what I've seen so far in terms of bubble plumes, they don't look as spectacular. Well, shall I say, there are not as many of them and not so obvious as the ones that I've shown you this afternoon. But what I should also say about the Svalbard area, which I didn't make much of, but is important, is that on the cruise, even in areas where we didn't see bubble plumes, we measured high methane concentration in the bottom 50 meters or so up just above the seabed. And other people on other work earlier, like Ellen Dam from RV in Bremerhaven, was already published for the southern part of Svalbard. Again, high concentrations of methane dissolved in the bottom water on the upper part of the continental slope. So there seems to be a very high signature of methane entering the water column somehow in this region.
Sven Titz, freelancer from Berlin. I'd like to know where the methane goes when it's dissolved in water. Is there a saturation of...
Oh, there's a saturation, but things happen to it before then. But there are chemists sitting to the left of me, and they'll probably answer this much better than I will.
For the microbiology, we can say, for example, there are processes where the microbes eat the methane. So the methane is dissolved in the water, and only that way they can access it, because it has to go through their cell membrane. And then they consume it. And the ones that live in the water column, they use oxygen. Like we breathe oxygen and burn our food, and so they use oxygen and burn the methane as an energy source. And then there are other microbes in the sediment that don't use oxygen. They use another chemical. It's sulfate that's dissolved in seawater, and they use that compound to consume the methane. And those two processes are like a microbial filter of methane, of large amounts of methane that want to enter the atmosphere from the seafloor. And the higher the water depth is about the sediment, the more effective actually this whole system is, because the more time it actually has to consume the methane. When you have very shallow water depth, there is a bigger chance that the methane will actually reach the atmosphere.
So what we know about saturation is that at atmospheric pressure, so on the sea surface, when we are on deck, we have the saturation of seawater is around 1 to 1.2 millimoles per liter. So at the moment these concentrations here were in nanomoles that we have in the seawater. So the ocean is very undersaturated, so it can take up a lot of and dissolve a lot of methane. And then the microbes will act and start to oxidize the methane, form CO2 in the end out of it. And what we also know is that gas bubbles, what Graham showed and said, is that at water depths of something like 400 or 500 meter depth, they will exchange the methane because the ocean is so undersaturated before they reach the surface. And on the other hand, the methane gas bubbles don't have a lot of other gases in there, like nitrogen, oxygen, and these gases go out of the water into the gas bubble. So most often that's what we've seen all the time in the Black Sea when we went there for several years. When we have gas bubbles reaching the surface, they contain mostly nitrogen actually, and only a few, maybe only a few percent methane are left or none. But what we know is that if we have shallower water depth, like something like 200 or 150 meters, then actually gas bubbles rise quick enough, and because it takes time to dissolve in the water, that methane by gas bubble transport still reaches the surface. So if we have quick emissions, large emissions, then there is a potential that the methane actually gets quick out of the ocean into the atmosphere.
One last question. Nobody?
Okay, and then, yes, good.
Has anyone actually ever observed a very large or catastrophic release of methane from this seabed, or is that just an assumption?
There is Ira Leifer, University of California, Santa Barbara, had an experiment where this was well demonstrated off the coast of California, where they were investigating a system which had been bubbling for some time, and were going to put a tracer to try and estimate the amount of water that was entrained and how fast the system was using, and had divers ready to put this in, and they had I think it was an aircraft set up as well as boats at the surface to observe this, and by accident, luck, though he says he anticipated a bit, the divers first reported that oh dear, the plumes, the bubble plumes have all stopped, and as a prelude to this massive outburst, the plumes stopped for a while, and then they suddenly all just went wild, and really large amounts of methane came out. And apparently, this is anecdotal, by the way, what he told me is that they have methane sensors around Los Angeles for industrial sources of methane, and because the wind was blowing from the west, they even picked up this methane burst.
So we've two other examples. One is also off California, Coal Oil Point, where they actually put tents onto these seeps and collect the methane off the US coast. And then in the North Sea there is one spot which is drilling from, forgot the company, was it Shell or so? BP? I forgot. It's a gas field, and they drilled into it, and then they did something wrong and had to abandon the hole, and for the last 20 years there now, methane, it's something like 50 or 80 meters water depth, it's like a whirlpool, and methane is continuously coming out of that gas reservoir. And I think there about 30% of the gas that still comes out is methane, so there also a lot of methane is dissolved in the water column.
Okay, thank you very much. I have to cut it short now because we have another one in 15 minutes. So thank you very much, Tina, Ben, and Matthias, for a very interesting day.